have a good weekend, man?
Yeah.
That's. How about you, Stuart? Did you have a good weekend?
It was good, yeah.
Did you stay here or are you at home?
I was here.
That's. Did you get outside at all?
A little bit, yeah.
That's.
It's nice though.
Yeah, it was really nice. It was really nice. Have you ever done Bear Fence Rock Scramble?
No, but I've heard of it.
Yeah, that's a fun afternoon. Yeah, up on Skyline Drive.
That was good.
If your folks ever come, that's a pretty fun time to spend with their parents. So they have to be a little athletic to do it, but
I
still.
think the one rock scramble, I think it was like Devil's Marble Yard or something.
Oh no, I haven't heard this one. Yeah.
I can't remember if it was here or if it was up in Pennsylvania, but that was a good one too. It was like just like the whole side of the mountain was like rocks the size of a car.
Oh wow. Okay.
And we,
Where are you from, Pennsylvania?
no, I have family up there.
Okay.
So I think it was up there.
I think that is Pennsylvania.
Yeah, and so we, there's like a trail that runs like the whole length of the, like up the side of the rock scramble. So if you can't like climb over the rocks, you can like hike up that.
Oh, that's really cool.
Yeah, that was a lot of fun.
Yeah, I haven't done. I forget. There's the big one on Skyline Drive. That's like a 9-mile loop. I'm just like, I don't know if I'm up for that. Okay. 43. Okay, yeah, 2 minutes. 2 minutes. And there's 2 people on, so that would be 4. So that's. I guess we had a test. There's Zachary. Okay, good. And we got 5 out of 35. Yeah, I went to my grandson's first birthday. They had a pumpkin patch down in Richmond, and so we were down there, and I'm just sure it was a super spreader. I'm just like, nobody was social distancing. My family just is not built for social distancing. You know, they hugs, people are wrestling. It's just like, okay. I think I was one of the few wearing a mask. Like, why are you wearing a mask? I'm like, well, I teach at JMU.
Yeah.
We've had a few cases here at JMU. It was nice to have Big Ten football back. That was nice.
Oh yeah.
That's
You Ohio State fan?
oh man, huge. I mean, they just put it in the water in Ohio. It's the only thing left in Ohio. You know, everything else is rusting and dying. So.
Good morning.
That's good morning. There's 2 more. Okay, now we can All right, it's 9:45. Let's stand up. I guess the 3 of you here. Just saying, guys, I have 3 in class today. 3. I can hold 22. So if you want to come to class, if you're like, Dr. Warren, I just learn better in class than not in class, I'm pretty sure there's room for you every day you want to be here. Every day you want to be here. So, you know, if not, if we get more than 22, I'll go outside or I'll find a big room. I'll find someplace. So yeah, if you're a student that really wants to be in class, please feel free to come to class. Okay, let's sit back down. Well, we now have quest 3 behind us. We have quest 3 behind us. We will probably have 2 more quests before break. Here's the kicker. In order to do that, that second quest has to be on that Friday before break. It has to be on that Friday before break. So if you're planning on leaving, make sure you leave. I may just make that day the quest, so I may just start it at 9:45, and again, it'll probably be like a 40-minute quest. So if you're gonna leave, make sure you're leaving around 11, not at 8 in the morning or the day before. Are we all on the same page? Are we all on the same page? Okay, because then I won't see you except in the grid. I won't see you guys except in the grid for the rest of the semester, Okay, so just laying it out there. When I say R of t, you say
Space curve.
space curve. When I say R of t, you say
Space curve.
space curve. Okay. I in fact have a space curve sitting over here. I've got a space curve. Oh yeah, web assigned. This Friday, 11:59. It's going to focus primarily on the TNB frame. It's going to focus primarily on that arc length TNB frame. That's section 13.3. That's section 13.3. Okay. When I say tangent line, you say. Very good, Stuart. R of C plus T times R prime of C. R of C is my position vector. R prime of C is my direction vector. Okay. And so what I've got here is I've got my space curve. I'm drawing it so that I'm believing that as I move along the domain of it, it's sliding along this part of this wire that's sitting in three-dimensional space. R prime of C points perpendicular to the curve. It's along the tangent line. It's a direction vector. R double prime of C, and this is kind of what we were talking about last time. R double prime of C points in the direction the curve is curving. Say that. R double prime of C points in the direction the curve is curving. Okay, so now let's go back to Math 236. Out of all the stuff you hated in Math 236, what was the thing you hated the most? There was lots of stuff to hate in 236, but what was the thing that you hated the most? How about infinite series? Do you remember infinite series? Do you remember those? To converge or not to converge? That is the question. Ratio test, root test. Taylor series. Do you remember Taylor series? You're like, Dr. Warren, I do not. Well, let me just remind you. If you got a function f of x, and you want to approximate this function at some point x equals c, the best polynomial to do this is my Taylor polynomial. The function f of x is approximately equal to f of c plus f prime of c times x minus c. Now that's your tangent line. That just ends up being your tangent line. And everybody remembers tangent line from AB or BC calculus. But not so many people remember what we'd call like the tangent parabola, which is if I add on f double prime of c times x minus c squared, this is a much better function than the tangent line. And then if I add on yet another term, f triple prime of c divided by 3 factorial, which is 6, times x minus c cubed, that's even much better still. That's like my tangent cubic. What would I add on if I wanted a tangent quartic? Well, it would be the fourth derivative at c divided not by 3 factorial, but 4 factorial times x minus c to the fourth. And the problem is there's not enough time at the end of 236. Teachers are usually gasping on air. Students are gasping on air. That most students, when they hit 237, don't realize how important Taylor series is. They just don't realize. How many people have a TI 84? How many people have a TI 80 something? How many people actually hit the sign button on that before? Sign and gotten a number. I mean, in engineering, have you ever done that? Sign of some number and gotten a button. How does the calculator get those digits? Do they fall from heaven? I mean, just think about it. Yeah, that's what most kids think. They take out their calculator, they push sign and 1, and digits come to the screen. And for all they know, maybe some math angel dropped those in there. They don't think that there's a mathematical algorithm. They don't think that there's a mathematical algorithm to get that approximation. And it all goes back to Taylor series. If you have a piece of scientific equipment that's spitting out numbers, chances are Taylor series is related to it. So I'm going to use Taylor series. What's a vector valued function? I hate you, Dr. Warren. What's a vector valued function? That's good. There's 30 of you. What's a vector valued function? Don't lay it all on them.
Order triple.
An order triple of, good Michael, an order triple of, Michael has
Real value functions.
3 real valued functions. Could I take the Taylor series? Of each of those 3 real valued functions at C? Could I take the Taylor series of each one of them? Okay, so what we can argue is that my space curve, R of t, if I want an approximation to it, the best quadratic approximation follows the Taylor series. It's R of c, which positions my curve, plus R prime of c times t minus c, plus R double prime of c over 2 times t minus c squared. This is the best quadratic approximation to my space curve. And so if you actually plotted this space curve, notice it is a factor space curve. Notice this approximation is a polynomial space curve. Say that. We've got this vector evaluated as c, a bunch of numbers. We take the derivative, we plug a c in, a bunch of numbers, times t minus c. That would be a line. That would be the tangent line. And this r double prime of c, that's a vector times this scalar. And so what you get is you get a parabola. You get a parabola sitting in the r prime, r double prime plane. Say that. And only the people here are saying that. I didn't see anybody's lips move at home. Okay, so what did I just say again? What did I just say?
The parabola in the r prime and the r double prime plane.
Hunter, thank you. Hunter. Picked up the ball. Okay? Sitting in the r prime, r double prime plane, and that's the best parabola in 3-dimensional space that approximates the curve. That is the best parabola in 3-dimensional space that approximates the curve. This plane that it sits in, the r prime of c, r double prime of c plane, is so important it gets its own name. It gets its own name. We call it the osculating plane. Having a 1.9 grade point average, I don't really know what osculate means. Okay, I have really no idea what that means. But to me, it just means it flies along and changes. It osculates, whatever that means. Okay, with the curve. I'm going to have a different plane. Doesn't make sense. I'm going to have a different plane here than here. Then I can have a different plane there and there to approximate the curve. This is when I really wished all of you were here and we had a piece of copper tubing here. Because it would be so easy. You're like, oh, Dr. Warren, this plane would be better here. Oh, no, but this plane would be better there. And you're up here, this plane would be better. It osculates. And again, I don't know what I'm saying. I'm making up my own meaning to it now. It changes. It changes. Now, when I say plane, you say, I hate you, Dr. Warren. When I say plane, you say...
N dot x minus a equals 0.
N dot x minus a equals 0. What's a in the game? What's a in the game?
position vector.
Position vector. What's in the game?
Normal vector.
Normal vector sits perpendicular to the curve. Okay, this is the osculating plane. Do I have a position vector? Look at the plane up here. Do I have a position vector? Do I have an A? Who's positioning this plane? R of C. So my A would be R of C. Now, how could I get in? If R prime of C and R double prime of C are sitting in that plane, how could I get a vector that sits perpendicular to that plane? Cross product. So my N for my osculating plane, my normal vector for my osculating plane is R prime of C cross R double prime of C. Now, I want to say this, because this jacked me. Okay, this normal vector has nothing to do with that normal vector right now. We call this the normal vector. But we're also calling this the normal vector, but they're two totally different things. This is the normal vector for the osculating plane. This normal vector is related, but it's not the same thing. Okay, so you said, I said plane, you said. If you guys can turn on your cameras, turn them on. I want to see. Luke, when I say plane, you say Luke, when I say plane, you say, Luke, are you drinking a beer? Oh, from Luke to everyone.
He said his microphone's still broken.
Okay, good. Are you still drinking a beer? Type that in. Are you drinking a beer or not? Luke, what did you type in the chat? What do you have there? Luke, are you smoking a joint? Luke. Okay, Luke. I'm believing your microphone's broke. When I say plane, you say... Not you, Luke. Sorry, I'm letting you off. When I say plane, you say... A equals 0. Do we have an N?
Yes.
Do we have an A?
Yes.
So if I'm thinking about the equation of my osculating plane, it would be R prime of C cross R double prime of C. There's my normal vector, dotted with the vector. Remember, it's a plane, so we have this x, y, z. Minus A, but A is R of C. And that's equal to 0. That's equal to 0. That gives you the equation of your oscillating plane. And this plane's really important. I mean, you don't think about it, but it's really important. You know, I'm a little pissed at this country right now. I'm a little pissed because, like, we have this virus just running through the country. But you know what we did this weekend? Do you know what we did? We landed, I guess it was on Friday, we landed a probe on a moving, does anybody know? We landed a probe on a moving asteroid. There's an asteroid out there that a probe of ours is sitting on right now, probing it. And the asteroid's not that big. It's not that big. And we just landed a probe on it. Do you think there might be some space curves involved? I'm just wondering. Do you think there might be some space curves involved? But then I watched the landing, and these 4 feet come down. These 4 feet come down, and they come in at a perfect 4. These 4 feet came down, and they came at almost at a perfect place where almost all 4 of them touched down at the exact same time. On this curved surface, almost 4. And then rocks kind of puffed up in the air, and I'm like, this is insane. I'm actually watching this take place. It's good. Do you think this plane might be important? Do you think this plane might be important as far as landing on something like that? You know, what plane? Can you imagine if it came in, here's the plane, this is like the surface, and they come in like this, you know what I mean? Like, bunk, we're done, probe over. $18 million, gone. Well, probably $30 million. Did you know we attacked Mars? Did you guys know we attacked Mars? About 20 years ago, we shot a probe right into Mars. By mistake. It was supposed to land on it, okay, but it went in with so much velocity that we just torpedoed Mars. You want to know why? Because Lockheed Martin sent all their measurements to NASA in English units, not metric units. And the scientists at NASA said, oh, well, these units must be in metric. And so we just attack Mars. A $30 million mistake. 30 million of my tax dollars, well, not all mine, mistake. Should I punish you? Should I punish you if you make small errors on your quests? Should I punish you? You're like, no, Dr. Warren. We can absorb $30 million. We can absorb. Okay, I'm just saying. Okay. All right, stop. Okay, how many people remember the movie? How many people remember the movie, the T&B movie that I created? That masterpiece. Do you guys remember that? I played that for you last time. Did you guys remember that? Do you guys remember that? Okay, so I'm going to play it again. Just for your fun. You're like, Dr. Warren, I'm now going to go to sleep.
Hey, Dr. Warren, is the plane ever still? Could you draw the plane for this curve?
Ooh, I could, but I didn't. I could, but I didn't. So, no, I didn't do that, but I should have. Oh, I gotta share. Wait. Okay, I'm sharing the screen for you guys.
All right, guys. What I'm trying to show here is they used to have Maple in on the classroom machines, but they don't have that software anymore. I think because of cost. But Maple has a really nice vector calculus package. So I kind of want to just show you this here. I'll just share my screen, and let me come up here. We'll execute this, but this is kind of a crazy space curve. If you look here, what I've got up here, I've got this.
You can tell I'm excited. You can tell I'm
T
excited.
times cosine of 3t.
I'm really proud of myself.
T times sine of 3t, and t squared minus 6 times t. Now imagine having to calculate the t and b vectors for that. Remember that capital T is the
what?
space curve's derivative divided by the norm.
Oh, that.
Okay. Then you got to calculate. N, which is t prime. So you're taking the derivative of that mess divided by its norm, and then you got to take the cross product of t and capital N to get b. But notice I'll do this just to show you the horror. Maple's going to do it. There is t.
Do you guys want to do that on the quest? Do you want to do that on the quest? Do you want to do that on the
Here
quest?
is n. Can you imagine that nightmare? Can you imagine that nightmare? I can calculate it. And here is b. But what's even more fun is I can get Maple to plot this for me, and you can see I'm running it between 0 and 3 pi, and I'm having it do 200 frames to
Just
show an animation.
Play
And
the
so
movie.
what we have here is you can kind of see it. It's a little hard to see the vectors. This vector right here is t. This is n, and this is b. And so what I'm going to do is I'm going to play the animation. And this is a fun curve. Imagine this being a roller coaster we just created. And again, the thing that's creating it is my space curve running between 0 and 3 pi. And now I'm going to do is come down and you guys can watch this frame fly through on the curve, and why it's such a much better frame to describe what the pilot's feeling.
We're bored.
than
We're
IJK.
bored. Just
You know,
push
I
play.
would sit down here, your J would sit there, and your K would there. So let me just go ahead and do this. So you can see it moving around that curve. You can see it moving down there, and you see how it's flying along my space curve. As we go through here, the tangent vector points to where I'm going, the n points to where I'm curving, and the b is describing how my pilot's wanting to move out of that osculating plane. So let me just do that again, play that again. And you can see how this is moving, how the n is pointing, the green vector is pointing to where we're curving the most, t is pointing to where we're going, and
Isn't that pretty cool right there? So this vector right here would be what? That vector right there would be what? You got a choice, t, n, or b. That vector would be t. Notice it's pointing tangent. This vector is n. This is the osculating plane also. R prime cross R double prime. This is the same plane. And this vector here is B. This vector here is B.
and my b up here is pointing to how I'm wanting to move away from that plane. How I'm
So if I wanted to land a probe right here, I want to land it along B. Does this make sense? I want to land this along B to get the most stable place to land my space probe. Okay, enough of that. Make me number one if I'm not number one. This is the equation of our, Dr. Morrell wasn't focused. This is our equation of our osculating plane. Okay, T is the definition of T. Now think about it, Quest. Have I burned you before with definitions versus theorems? Okay, so T is defined to be, capital T is defined to be the derivative of the space curve divided by its norm. Okay? And then N is defined, the normal vector, which is not quite like this normal vector. Okay? The normal vector is defined to be the derivative of T. Now guys, focus. T, N, and B are a lot like IJ and K. They're a lot like IJ and K. They're all unit vectors, and they all sit perpendicular to each other. Is it nice that IJ and K sit perpendicular to each other when you're measuring? And the same thing's true up here on the space curve. So T prime is perpendicular to T. Say that. And then I could ask why, and you would say, I don't remember, Dr. Warren. It's because they're unit vectors. What's the derivative of 1? 0. And so we're able to use that dot product identity, that the norm of t squared is t dot t, take the derivative of that, and find that these are perpendicular to each other. These are perpendicular to each other. And then I want a unit vector, so I've got to divide it by its, norm. This is 1, the cross product's not going to change the length. It's also going to be 1. This is the way the book wants you to calculate this. It is a nightmare. Even for simple functions. I have found what I consider a better way. To calculate the T and B frame that I think takes about half the effort of that. Let's just look at the horror for a second. Give me a space curve. Just give me a space curve. Give me a space curve. Any space curve. Give me a space curve. And we gotta have some trig in it. You guys let me know. So R of T, let's make it sine of T. There's my first sine of T. What's my next vector value function? What's my next real value function in this thing? My order triple.
3t squared.
3t squared. And then maybe let's do
ln of t.
yeah, maybe ln of T. Vector value function, true or false? True or false? True or false? Vector value function, true or false? The domain's all real numbers, true or false? The domain's all real numbers, true or false? The domain is all real numbers. False, because of that beast. That's only defined for t greater than 0. Okay, now let's find capital T. So I would do what with this thing? If I want to find capital T, what do? Take the derivative. So you guys take the derivative. Let me see if I'm annoying everybody. Looks black and dark. I'm hoping on a quest you would be done taking the derivative. I'm hoping on a quest you'd be done taking the derivative. And so what do you get for r prime of t? What do you get, guys? What do you get? What do you get for r prime of t? What do you get? Cosine of t. 6t and 1 over t. Now, is this capital T? Is this capital T? Is this capital T? And you're like, no, it points in the same direction as capital T, because this is a scalar. So T and capital T, T and capital R prime, T and R prime point in the same direction, because this is a scalar multiplication. So now let's find capital T. Capital T of t would be equal to, capital T of t would be equal to the cosine of t, 6t, 1 over t, and then divided by the, help me out, divided by the square root of cosine squared of t, 36t squared, and then
1 over t squared.
1 over t squared. How many people are following? How many people are following me? How many people are following me? Okay, now how do we get capital N? How do we get capital N? How do you get capital N? I'll keep asking. How do you get capital N according to the book? The derivative of that. Do you want to take the derivative of that? Do you want to take the derivative of that? Do you want to take the derivative of that? Because this is a scalar. It would go to this function, and that function. Then you would have to take the derivative of it, and then you would have to divide it by its norm, and then you would take the cross product. Then you would take the cross product. Do you see how this can be a nightmare? Do you guys get that this could be a nightmare? Can you imagine doing this on a quest? Can you imagine doing this on a 40-minute quest?
Take the whole quest.
It would take a lot of the quest, and what's the probability of you screwing up? You've got all these derivatives to take. What's the probability that you might screw up?
100%.
100%. Okay, what's your name again?
Patrick.
Patrick's like 100%. Okay, and then let's say you screw up here. Is that going to screw up everything else? Is that going to screw up everything else? But this is the way the book wants you to do it. But I found an easier way, and I don't think anybody else that I know teaches it this way. So this is the way I'm going to have us calculate this. Let's not do this. Okay. Notice T prime points perpendicular to T. My T and B, that T cross N is B, T cross N is B, N cross B is T, and B cross T is N. And this is what I'm going to exploit. This is what I'm going to exploit. We're not going to calculate N by its definition. We're not going to calculate N by its definition. Okay, so we know that T, capital T, is R prime divided by the norm of R prime. True or false? True or false? True or false? True. Okay. The numerator here is a vector. The denominator is a scalar. So I'm going to rewrite this as the scalar times the vector. Now remember, taking the derivative of the vector wasn't so bad. The thing that's bad is taking the derivative of that scalar with that square root and those squares. So now, do we have a product rule in calculus, in vector calculus? Do we have a product rule? Do we have a product rule for dot products? Do we have a product rule for dot products? Do we have a product rule for cross products? Do we have a product rule for cross products? Do we have a product rule for a scalar times a vector, our three multiplications? And the answer is yes. Let's use that last one. Then t prime would be equal to the derivative of that. But now let's use product rule. That would be, I am not taking this derivative explicitly. I hate this. So I'll just write it as the derivative of the first times the derivative of the first times the second. What's in the middle of our product rule? Plus the first, the scalar, times the derivative of the second. But what represents the derivative of r prime? What represents the derivative of r prime?
R double prime.
R double prime. R double prime. Okay. Now, what I want to do is I want to take the cross product of this. I want to take the cross product of this with r prime. I'm going to take the cross product of this with r prime. I'll have t prime cross r prime. But that would be equal to taking the cross product of this. Now let's go back, I'm crawling on my knees. What did we show this was equal to? What did we show A cross B plus C was equal to? What did we show that was equal to? A cross B plus A cross C. Okay, so now notice I've got this scalar times that vector, and this scalar times that vector. But remember, one of our identities is that if you've got A cross alpha D, this is the same thing as alpha A cross D. It doesn't matter where that scalar is. So this would be equal to this scalar I don't want to calculate. I know you're not focused at all. This scalar I don't want to calculate times r prime cross r prime plus that. So all I've done from the equation above, is done what to both sides? All I've done from the equation above is done what to both sides? Very good, David. I crossed with r prime, and then I distributed. How many people are with me? How many people are with me so far? How many are kind of with me? So what did you do again, Dr. Warren? Okay, I just started with t, and then I took the derivative, and I used what rule? Product rule, and then I did what to both sides? Crossed r prime and used my distributed properties. Used some properties that we had back in chapter 12. Okay, but what do I know about A cross A? What do you remember about A cross A? What do you guys remember about A cross A? Anyone? What do you know about A cross A? It would be the norm of, if you have A cross A, it's equal to the norm of, well, the norm of this would be the norm of A times the norm of A times the sine of the angle in between them. But the sine of the angle in between them is 0. Sine of 0 is 0. So norm of A cross A is 0. A cross A is 0. A cross A is the 0. A cross A is the 0 vector. So that means this guy with this horrible derivative is this guy with the horrible derivative is 0. And that's why we did this. You're like, Dr. Warren, why are we doing this? Because it gets rid of this guy. Okay, Dr. Warren, I'm still not getting it. I'm still not getting it. Now I have to erase. I guess I'm going to go over here. Sorry. Now we have that T prime cross R prime is the same thing as 1 over the norm of R prime, R double prime, cross R prime. Now I know it's taking a bit. I know it's taking some time. But how many people are following? I mean, I know it's been a little bit of a being out in Doug with the woods when he's taking on that Japanese concentration camp walk. Okay, I know it's a little bit like that. That's what you feel like. But I want to tell you again, all I did was start with the definition of T, took the derivative for T prime, which is what I would need, did some product rule, crossed both sides, then used the fact that this would be 0. Okay, now this is the trick. This is if you're going to miss it, you're going to miss it. Someone have you stand up so you don't miss it. Stand up, stand up, stand up. You know you need to stand up. You know you need to stand up. Haley was already standing, I think. Okay. Stretch. Stretch. Look at the time. Look at the time. What time does class end? What time does class end?
11.
Okay, what time is it?
10:24.
10:24. Okay, sit back down. Good. We're good. Okay, notice, I don't know why I think if I say it that tone, you guys, that's good teaching. Just say it like real slow and notice, like that's what you're gonna learn. Now notice that T is R prime divided by its norm. Now the norm is positive, true or false? True. So we ain't going to change the direction of R prime. True or false? True. T and R prime point in the same direction. True or false?
True.
Really the same vector, just scale a little bit. Now notice N is T prime divided by the norm of T prime. So N is going to point in the same direction as T prime. Well, if I looked at B is equal to, by definition, B is equal to, Dr. Moore, stop it. T cross N. Now I know this is not B, but I gotta ask, if I did T prime, if I did R prime cross T prime, does R prime point in the same direction as T? Does R prime point in the same direction as T? And does T prime point in the same direction as N? Then R prime cross T prime would point in the same direction as B. It wouldn't be B. But would it point in the same direction as B? And that's what we're going to exploit. Because I know, and I guess I did it wrong, I've got T prime, I have, over here I've got what, guys? Over here I have what? Bad teaching moment. Over here I have what? T prime cross R prime. But the good teacher would have probably ended up with a R prime cross T prime. But guys, if I switch this, and switch this, am I still in good shape? If I just switch this and switch this is a positive scalar. If I switch this, it changes a minus. If I switch that, it changes it to a minus. And so those minuses would cancel out. So this is not great teaching. So this points in the same direction. This points in the same direction as capital B. This is a positive scalar. That is a positive scalar. So this vector right here also points in the same direction as, this vector right here also points in the same direction as capital B. So write that down. R prime cross R double prime. R prime cross R double prime points in the same direction as capital B. R prime, moral of the story is, R prime cross R double prime points in the same direction as B. And that's the way we avoid having to take the derivatives of these scalars. Okay, so let me see, what can I erase? I guess I gotta erase this. How many people like step-by-step methods? How many people like step-by-step methods? How many people like step-by-step methods? If I said, here's a step-by-step method for calculating the T and B frame, okay, at a point C. That's what I'm going to give you now. Step by step for calculating T of C, N of C, and B of C at the point T equals C. And this is what I'll ask you to do on a test. This is what I'll ask you to do on a quest. So what will I ask you to do on a quest? T and B frame at the point T equals C. Step 1. Calculate R prime of T. How many people think that, like, if I give you a space curve, how many people think they could do that? How many people think they could do that? If I give you a space curve, how many people are on board that they could actually? Okay, step 2. Calculate R double prime of T. Now this might get messy, but not in Calc 3. What did I just say? It's not going to get messy in Calc 3 because they know how hard this is. They're going to give you nice, easy functions to take the derivatives of. How many people are on board for step 1 and step 2? How many people are like, Dr. Warren, I'm following you with step 1 and step 2? Okay, step 3. Put beside this step you guys read it. What, they can't read it at home. Read that. What does that say?
Holy crap.
Okay, so Rhett, go up to the camera and say that. Holy crap. Okay, write that down. Yeah, okay. Say, because guys, if you forget step 3, it's really holy crap. You just torpedoed the problem. Do you think this is an important step? It's the holy what? It's the holy what step?
Holy crap.
The holy crap step. Okay. This is in capital letters. Plug in C. Plug in C to get R prime of C and R double prime of C. Now look, Dr. Warren, who cares? You care. Because the moment you plug C in, this becomes not a vector of functions, it becomes a vector of, the moment you plug C in, It's no longer a vector of functions, but it's a vector of numbers. And this would also be a vector of numbers. And that's what makes this a lot simpler. Step 4, while your brain's still going, calculate R prime of C cross R double prime of C. But now, because of step 3, it's the cross product of vectors of numbers. How many people can take cross products now? How many people can you take cross products, especially if they're numbers? I mean, if they're functions, it's still bad, but it's not impossible. But you just don't have time on a quest to do that. But you do have time to take cross products. Okay, now let's see if you guys learned anything. This vector points in the same direction as, this vector points in the same direction as
Vector B.
This points in the same direction as B. Can we now get B? Can we now get B? I want a unit vector that points in this direction. What would I do? I want a unit vector that points in this direction. What would I do?
Divided by its norm.
But divided by its norm. So you guys write down step 5. You guys write down step 5. Capital B of C equals, and you guys write down what it is. Capital B of C equals, and you write down what it is. Okay, hopefully everybody has this. How many people had a fraction? How many people had a fraction? How many people had a fraction? The numerator is a vector. It's just the vector you got from step 4, and then you divide it by its norm. Again, provided you've done step 3, you're not taking the norm. You're not taking the norm of functions. You're taking the norm of numbers. You're taking the norm of numbers. If I gave you a calculator, could you do that? If I gave you a calculator, could you do that? You know, like, but Dr. Warren, on your tests, you don't let us use calculators. And you should say, thank you, Dr. Warren. So say that. Thank you for not letting me use a calculator.
Thank you for telling me now the calculator.
Because that means I've got to make it simple enough that you don't need a calculator. So you're not writing down a bunch of digits. That's not calculus. That's scribing. What the calculator gives you, which you don't even know how it does it. Just like, I don't know, does it? I got it. How does it work? Magic. It works with magic. No, Taylor series, Taylor series, Taylor series. Okay, so now we're here. Now we want to find T, N, B. Who do we have? B. Is T that hard? Is T that hard, guys? Is T that hard? So if I wanted to find T of C, in step 6, provided I've done step 3, in step 1, that's not bad. T of C, T evaluated at C, is just R prime of C, which you've already done. You've already done that there, divided by the norm of R prime of C. Divided by the norm of R prime of C. Dr. Warren, could you read that for me again? I'm not in the classroom. Is R prime of C divided by the norm of R prime of C? And guys, I just want to say again, there's 4 people in class. If you're somebody who would rather be in class, I'm almost certain there's room. Every day you want to be here, feel free to come. I'm almost certain we won't fill this place. And if we do, I will find a bigger place in this building, okay, to have us. Okay, do we have T? Do we have T? Do we have T?
Yes.
Do we have B? Do we have B? Do we have B?
Yes.
How do we get in? 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 You're like, Oh, Dr. Warren, you boxed that for me over here. You go, how do we get in? We do
Cross product.
the cross product. So then my last step, step 7, is I get N of C by taking B of C cross T of C. So Dr. Warren, why do we do it this way? Because we never have to take the derivative of that norm. Do you guys realize how nasty that would be, taking the derivative of that norm? So we're trading derivatives for cross products. Is that a good trade? Is that a good trade on a quest? Is that a good trade? Trading derivatives, you're like, Dr. Warren, I don't like cross products. I should make you do one of these by hand. Then you would come back and you'd be like, bless you, Dr. Warren, bless you, bless you, bless you. Okay, don't look at your notes, don't look at the board. Don't look at the notes, don't look at the board. What's step 1?
R prime of C.
R prime of T. What's step 2?
R
Could you do that? Could you do that for a curve? Could you do that for a curve? What's step 3? The holy crap step. So you now have vectors of numbers. You now have vectors of numbers. What's step 4?
Cross product.
Cross product. Is it R prime cross R double prime or R double prime cross R prime?
R prime cross R double prime.
R prime cross R double prime. What's step 5? Get B by taking that cross product and dividing it by its norm. Okay, step 6 is is that hard? If you've done step 3, is this that hard? Is this that hard? And then what's the last step? You get in by taking the cross product of the vectors you get in these 2 steps. How many people think they could do that? How many people think they could do that? Okay, let's see if you remember what we had on the board earlier. What's the equation of the osculating plane? What's the equation of the osculating plane? What's the equation? Don't you look at your notes. What's the equation of the osculating plane? R prime cross R double prime of C dotted with X minus R of C equals 0. So, would it be hard? Would it be hard to get the osculating plane? Would you already have done most of the work? Would you already have done most of the work to get that normal vector sitting off that plane? So do you see how I could write this as one question? Do you see how I could write this as one long question? Just a hint, just a hint. Do you see how I could write this as one long? You guys are now in Calc 3. There should be alerts going off in your head. I get it as freshmen. A teacher says, oh, I'd pay attention to this. And you're like, oh, I don't think I care. I'm not writing anything down. But by Calc 3, if a teacher says, could I write this as one long question? You should put in a star. I guarantee Rachel immediately put a star. Exclamation point, exclamation point, exclamation point. You know, this is... Okay. How much time do I have left? How much time do I have left?
20 minutes.
20 minutes, okay. One last concept. One last concept. And then we're going to end this chapter. It's called curvature. Write that down. Curvature. What's it called?
Curvature.
Curvature. Okay. Guess what it has to do with? I mean, if you had to guess, what do you think it has to do with?
Curves.
Curves. It describes how the curve is, for lack of anything better, curving. It describes, it's a quantity that describes how the curve is curving. So curvature does what, basically? Basically, curvature does what? Okay, first of all, it's a number. First of all, it's a number. It's a numerical value. It's not a vector. It's a number. Okay, if you're designing an amusement park ride, or you're sending an astronaut on a ride, and your curvature is high, you could really hurt that person. So if somebody says, this has got pretty high curvature, you should be like, whoa, 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 okay, all right. if the curvature is low, it means it looks more like a line. And you're like, oh, that's gonna be pretty easy. That's not really gonna hurt anybody. It's not gonna be any fun, okay? But it's not gonna hurt anybody. Like if a curvature is 5, you're kind of like, whoa. The curvature is 0.1, you're like, it's pretty easy. That's pretty simple. Okay, so this is the definition of curvature. What did I just say?
What's the definition of curvature?
Let me just tell you right now, you're not gonna like it. You're not gonna like the definition. You take the unit tangent at a point, but you think of it as a function of arc length, not as a function of time. Because you want to describe how the curve is curving. Time's not going to work for you. Time is telling you how fast you're moving along that thing. You're looking at the unit tangent as a function of arc length. And it's described as the derivative of the tangent vector with respect to arc length. Now guys, you're in Calc 3. Chances are your parents are asking you what calculus is about. And you say, well, calculus is about, Dad, limits, derivatives, and integrals, oh my. And he goes, what's a limit about? And you'd be like, you don't want to know, Dad. You don't want to know. Everything's defined in terms of in calculus, everything's defined in terms of a limit. If he asks what a derivative is, you should be able to tell him. And if you tell him the slope of the tangent line, if you say, Dad, it's the slope of the tangent line, that's not what it's about. It describes rate of change. Say that.
It describes rate of change.
It describes rate of change. If you say df by dx, f prime of x, it's saying how f is changing. How f is changing with respect to x. Like for example, if f of t is dollars of a stock at time t, then f prime of t would describe how the dollars are changing with respect to time. Do you think this is an important quantity to your dad? Think this is an important quantity to your dad? Okay? So here we're saying how the tangent vectors changing with respect to the arc length. Arc length is nice because it chops up the curve into equally spaced points in the domain. So we're saying, how does this tangent vector change? How does this tangent vector change as we move along here? If there's more of a curve, then this tangent vector is going to change more. That unit tangent is going to change more. If it's a nice sweeping curve, it's not going to change too much. That tangent vector is going to basically remain the same. But I said the curvature is not a vector, the curvature is a scalar. So that's the curvature. The curvature is the norm of the derivative of the tangent vector with respect to the arc length. Now here's the thing. You all hate arc length. You all hate it. Arc length is defined in terms of an integral. Arc length is defined in terms of an integral. So we avoid that like the plague. Let's just see. I gotta test you. Is there anybody out of 35 of you, is there any one of you that remembers the arc length function? Is there any one of you? If you got a space curve on the domain A to B, what's the arc length at T? It's an integral.
From A to B.
Not to A to B. I like that though, Rhett. From A to T. Very good, Stuart. Now what are we integrating?
R of T.
Close. R of Z. It's actually R prime of Z. And it's the norm of R prime of Z dz. And you're like, I hate you, Dr. Warren, I hate you. This is S of t. Let's see if you remember your fundamental theorem in calculus. Then what's S prime of t equal to? 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 I'll keep asking. Then what's S prime of t equal to?
Norm of R prime of Z.
Not of z, but
No, sorry, T.
very good, Gordon, very good. The norm of R prime of t. So what's ds by dt? You're like, well, that's the same thing, Dr. Warren, just different notation. And so this is the way we typically calculate. This is the way we typically calculate this. We think about t as being function of arc length. What did I just say?
Think of t as being a function of arc length.
That's one person. We think of t as being a function of arc length. Stand up, stand up, stand up. I can sense the boredom. I can sense the boredom. I can sense the boredom. Dr. Will you try listening to you for an hour? You try that. How many think the dashboard might be a little higher next weekend, next Monday? How many people think the dashboard might be a little higher next Monday? After Halloween. How many people think that might happen? I mean, let's just sit back down. Let's sit back down. No playing. No playing. No playing. There's no trick-or-treating. No trick-or-treating. Alex, no trick-or-treating. No trick-or-treating. Roberto, no trick-or-treating. Caitlin, no trick-or-treating. Okay. Greer, no trick-or-treating. Zach, you can trick-or-treat. Zach, you can trick-or-treat. I think you'd be safe. I don't trust Cosmo. I don't think. Okay. All right. Okay. As t goes, does the arc length get longer? As you move along the space curve in time, does the arc length get longer? Which means it's an increasing function. Which means it has an inverse. So I can think about s as being a function of t. And so now, you guys are going to help me. This is t evaluated at s of t. Now I'm going to take the derivative of this with respect to t. And I'm going to try to come up with an easier formula. I'm going to take the derivative of this with respect to t. What rule am I going to need, 235ers? What rule am I going to need to take that derivative? Chain rule. So it's the derivative of the mommy evaluated at the fetus times the derivative of the fetus. That's chain rule. Who's the mommy? T. So it's going to be the derivative of the mommy in Leibniz notation. It's going to be dt by d chain rule. dt by ds times
ds dt.
ds dt is equal to dt dt. And you're like, hey, Dr. Warren, look, these cancel like fractions. And I'm like, no. It's chain rule and, does anybody remember the other thing? It makes a wonderful true false. It's chain rule and nobody. I spent an entire lecture on it. It's chain rule and inverse functions. It's chain rule and inverse functions. Okay. Now, does anybody see ds by dt other than here in the room? Does anybody see ds by dt? Anybody see ds by dt anywhere else in the room?
The norm of R prime of t.
So this is like Rhett's saying here, you guys at home are saying that's blurry, times the norm of R prime of t. So dt by dt, which I can write as t prime of t, I mean, because that's with respect to time, Can you guys see that at home? Can you guys see that at home? Is that still visible? Am I too far off the board? T prime of t is dt by dt, which is dt by ds times ds I dt. But this is dt by ds times r prime of t. Dr. Warren, I hate you. Well, then the norm of t prime of t would be equal to the norm of this, which would be equal to the norm of this times this scalar, which would be equal to the norm of that. And this is what allows us to calculate this curvature in an easier formula. Look at that last line. Look at that last line. What represents the curvature? Where's the norm of dt by ds? Where's the norm of dt by ds? Look at the last line. Where's the norm of dt by ds? Could you circle it? Could you circle it in your notes? In this last line, could you circle the norm of dt by ds? We're like, Dr. Warren, it's here. It's also here. And so we've just shown this, that the norm of t prime of t is equal to the norm of dt by ds times the norm of r prime of t. And so a simpler way to calculate curvature is, to avoid the arc length altogether, it's equal to t prime of t's norm divided by the norm of r prime of t. So the book will ask you to calculate it this way. They use this letter. I don't know where this came from in history for the curvature. They use kappa. It's a Greek letter. It looks like a K. In fact, I draw it to look like a K. Kappa is our curvature. And kappa changes as time changes. Now, like Dr. Warren, but I don't want to take the derivative of t. Well, we can also show, and this is the way I want you guys calculating it. We can also show that kappa is equal to the norm of r prime cross r double prime divided by the norm of r prime cubed. And that's the way I want you guys calculating it. Now look back in your six-step method. Would have you already calculated that? Would you have already calculated the numerator? And could you get the denominator pretty easily? So this is the way I want you calculating it. I don't have time to show you why, but we basically did this. If you go back and look at your notes, you'll see where we did t prime, and remember we did r prime cross t prime. Do you remember that, where we had r prime cross? Go back and look at your notes. And see where you had r prime cross t prime. Go back and look at your notes. We had r prime cross t prime, when it was all said and done, was equal to, remember, things vanished. Does anybody remember, what do we have that was equal? What do you think it was t prime cross r prime? I forget what we had. It was equal to 1 over the norm of r prime
Double prime.
r prime cross r double prime. Okay, so now if I took the norm of this, it'd be like looking at the norm of that. But notice that's kind of my numerator. I've got this 1 over r prime. Like, where's that one coming from, Dr. Warren? Okay, this is tough. I'm trying to land this plane in the water, okay? I'm jettisoning everything. The norm of A cross B is equal to, does anybody remember? The norm of A cross B is equal to the norm of A times the norm of B times the sine of theta, sine of the angle in between them. So this would be the same thing as the norm of R prime times the norm of T prime times sine of the angle in between them. But R prime points in the same direction as T, and T prime is perpendicular to T. Remember that, because this is a unit vector. So T prime would be perpendicular to R prime also. They point in the same direction. So if they're perpendicular, what's the angle between them? If they're perpendicular, what's the angle between them? 90 degrees. What's the sine of 90 degrees? 1. So this is a 1. And do you see now how if I want the norm of T prime divided by the norm of R prime, but I don't have division here, I've got times. So then I would divide it and divide it again. And that's where my cube is coming from. That's where my cube is coming from. So down and dirty. Now, like Dr. Warren, will we have to rederive that on a quest? Guys, no. That would be the entire quest. That would be the entire. Would you have to use the 6-step method? Would you have to use the 6-step method?
Yes.
Yeah.
Notice, does this fall pretty easily from the 6-step method? Does curvature fall pretty easily from the 6-step method?
Yeah.
Okay, so let me end class with this. See how much time I've got. 2 minutes. Write this down. If kappa is big, the curve is curving a lot at that point. If kappa is big, you could hurt somebody. You're putting a lot of g-forces on that person if kappa is big. If kappa is small, it's pretty good because it's almost like a line. The smaller kappa, the better, as far as writing. Not exciting, but okay. And we'll call that chapter 13. We'll call that chapter 13. On Wednesday, we're going to start chapter 14. On Wednesday, we're going to start chapter 14. Do we have a quest this week? Do you have a web assign this week?
Yes.
Will you have a quest next week? Yes. Thanks, guys. Thanks for playing. This is a tough lecture. Thanks, guys, for coming. It's so nice to have students teach.
Have a good one, Dr. Warren.
See you guys.